Okay, so we're going to a lot of trouble to calculate energy levels, allow transitions, line positions. For the most part, though, we go to databases. So I think you have to understand the concepts, but then you go use a database. Especially when you go to a triatomic molecule, CO2, water, you just go to a databases that give you line positions. Trouble is those databases may not give you good line strength information. And so those databases are usually limited to low temperatures. So for example, if you want to know, well, what are the lines that are present at 8,000 Kelvin, the databases may be incomplete. So you're right. So for right now, we're just understanding things. In practice, you don't have to calculate these things. You just go into the database. But you'll need to understand the notation and which line is which and what does it mean and have a physical feel. But you're right, we use HyTran as one database. It's a common one. There's others. Those are mostly visible infrared databases, electronic. The line strengths now? Yeah, so the line strengths are such that if you know them at any temperature, you can calculate them at any other temperature. So the line strength is a temperature-dependent quantity. Remember, it really rests on the Boltzmann fraction. So if you know it at any temperature, you can calculate it at another temperature. So there, in that regard, HyTran is fine if the lines are there. But I'm not sure it answers your question. But for the most part, positions don't change, but the strengths change with temperature. Okay, I'm going to get started even though not everyone is back. Let's hope for the best. There's some units that you have to keep track of or learn about when you do these things. There's a question about how many of these vibrational levels do we have. Here's a little example here to tell you that it might be of the order of 40 or 50 vibrational levels in a diatomic molecule. Okay, we use something called the Born-Oppenheim approximation. This is the essence of why we can separate, we assume, that the rotational and vibrational energies are distinct and separated. They don't know about each other. That's an approximation that simplifies our life immensely. It's not exactly correct, but it's pretty correct. In this model, we have the selection rules of delta V of 1 and delta J of 1. Now, when you go to combined vibration and rotation, delta J can now be plus or minus 1. The upper energy level is always way up here. Now delta J can be either plus 1 or minus 1. In pure rotation, it's only plus 1. Now the positions are always the differences between the energy levels, which we usually denote with a capital T. T is usually the so-called term energy, upper state, lower state, and the frequency is always going to be just the difference in the states. That's this conservation of energy. So now when we do this for vibration, we're going to add up rotation. We're going to take the rigid rotor and the simple harmonic oscillator, and we're going to add F. I should have also said F is used for rotation, G is used for vibration. So we put those together. That's the energy of our rotating, vibrating molecule. Here's our selection rules, and that means that when we have a transition from this state here, V of 0 to J, you can either go plus 1 or minus 1. And here's the notation again. The notation for delta J is J upper minus J lower. It's P when delta J is minus 1, and it's R when delta J is plus 1. So there's two possibilities. Notice that the R arrow is longer, higher energy, higher frequency. So when you plot the transmission spectrum, transmission probabilities, I think that should have been the absorption probabilities, sorry about that, versus frequency, normalized to the Zener and divided by B, there's two branches, P and the R. The R is always the long arrow. Higher frequency is always the R. And these parentheses tell you the initial value of J. So R of 0, R can go from 0. R can go from 0. If this J double prime is 0. P cannot go from 0 because you can't go to minus 1. So the minimum value of P is a 1. So that's what the spectrum looks like and explains the branches that we've been talking about as we go. Here's the notation in spectroscopy. The branches are called OPQRS, so they're centered at Q. Delta J is 0, plus 1, plus 2, minus 1, minus 2, OPQRS. We're dealing with only P and R right now. Pretty soon we'll find there's a possibility of a Q, And when you go to Raman spectroscopy, you can have O's and S's. So that's universal. The R branch transitions now are the difference between the G's again, plus the differences in the B's. And so we have an equation for the lines that depends upon the level of anharmonicity. So if it's a simple harmonic oscillator, this delta G is always a constant. But when it's an anharmonic oscillator, you have a correction term that depends upon which vibrational levels you're in. So as soon as you go to the anharmonic oscillator, you have to be more careful about the level of V. But what about the spacing of these lines? The spacing of the lines is still going to be 2B. So even though we're now in the infrared, the spacing of the lines is still going to be 2B because we still have delta J of 1 rule. We can still define now we can talk about the spacing between the peaks of the P and the R, another way of thinking about temperature. So now, okay, here's the absorption spectrum. Okay, so it's transition probabilities. Fine. Here's the absorption spectrum for a molecule in B double prime of 0. So now omega minus omega E, because remember omega E is delta V divided by 2B. So if we march along this axis, we see lines at intervals of 1, but the spacing is always 2B. All of these lines is a branch, our branch. The total combination is a band. That's called here we go again. All right. Oh, man. Skate through today and get another computer. I had to reboot, so everything is all. Okay, so this is throwing me off a little bit. Now, when we get rid of the rigid rotor, what are we going to expect? The line spacing is no longer exactly 2B. It'll vary slightly. But it's always the case that the total energy is G plus F. And you just have to decide if you're going to use rigid rotor or an anharmonic oscillator or corrected terms. So now if we use the correct expression for R, so there's the omega that depends upon V plus now these terms. So if it's rigid rotor, B upper and B lower are the same, and that term goes away. And delta B here is going to be 2. So you can see this is what happens. As you go up, as you remove the rigid rotor harmonic oscillator, you have to worry about the fact that B depends slightly on V. So these are just corrections. And, okay, so what that means, I hope you can see this. There's the solid line, and then there's the dashed line. The dashed line would be the ideal line, harmonic oscillator, rigid rotor, and the corrected line. So basically, you get slight adjustments to the line positions, not the strengths, the line positions. So that means that if you plot a spectrum like this, and you plot the frequencies now versus J, the R branch grows higher frequency. That's the long arrow. You eventually reach a place because it turns back because of that delta B term, which is negative. So on the R branch side, the line spacing gets smaller, and on the P branch side, the line spacing gets bigger. And so that means eventually you reach a place where the band turns back on itself. And when that happens, it's called a band hit. So in fact, if you were to plot out the entire spectrum for the P branch and the R branch, you'd see that the R branch lines come back on themselves. The P branch lines get further and further apart, increasing spacing, decreasing spacing. So if you ever see a band head, the edge of the line, you'll know you've got a measure of this non-rigid behavior. However, you can calculate where that is. So you can take the derivative in the R branch with respect to J and set it equal to 0, and you'll find that it'll occur at a value of J, approximately B over alpha. Remember, alpha was about, B was about 100 times bigger than alpha. So it would only occur at J of about 100. But in normal conditions, you don't get out to J of 100 because the temperatures are hot enough. You'll only can see this if you can populate J of 100. means you got to be at very high temperature. You look at the Boltzmann fraction for J of 100, you better be at really high temperatures or the population is 0. So it's not often observed, but it's present. Okay, so now I talked about how you could determine B by looking at the spacing of lines in the microwave spectrum. How would you go about determining the other parameters? At this level, right now, there's 4 terms that determine the positions of lines: B, alpha, omega, and X. Those are the 4 terms. How could you measure those? Well, if you looked at the spectrum and you looked at the null gap for the 0 to 1 band and the 0 to 2 band, you'd have 2 expressions and 2 unknowns. So you can use the band origin or null gap data to determine omega and X. So if you had the spectrum, and we do this in my lab class, you measure the spectrum with the FTIR, you find these numbers, these band centers, and you've immediately determined omega E and Xe. 2 equations, 2 unknowns. Now, but we still have to solve for B. We still have to solve for B and alpha. We do that by fitting the positions of the lines to what's called the 4-track parabola. And if you fit the expression for the lines, you can fit them as a function of quantity m, which is either j plus 1 or minus j, depending on which branch you're in. So you fit all of the lines to this pattern, and from that, again, you can determine the 2 different b's, and therefore be and alpha. So there's a simple way in a laboratory to determine these numbers if they're not known. Usually they're known, and you look them up in the tables, and you calculate the spectrum. So I had a question here. So for the most part, you can calculate the spectrum, but for the most part, people just use tables. You just look it up. Want carbon monoxide, find the carbon monoxide table. And it'll just tell you the positions. So remember, positions, strengths, and shapes. The tables will give you positions. They won't necessarily give you strengths, and they won't tell you anything about shape, really. So here's our improved model. It just recognizes all the corrections that we have to do. There's a third way of determining these numbers. It's called the method of common states. Imagine you have the line positions, the numbers. Now you can think about it this way. Pick the 2 transitions that have the same upper state. They would come from here, and they'd come from here. If you have your positions, you can take the difference between these 2 lines, and you've just determined that delta E, which is a function only of B in this lower state. Method of common lower states, you imagine the same lower state transition, you go to 2 different upper states. Take the difference in those line positions, and you just determine B prime. So there's a family of different strategies for how you can determine the 4 parameters in the right now, there's only 4 parameters in the spectrum for the positions, and you can do it all. Okay, isotope effects, I made the key point that the spacing of these nuclei depends on electrical forces, which does not change when you change the isotope. So you change the isotope and you change the spacing, and you can use that also as a way of getting at the parameters. So if we do this for carbon monoxide, the reduced mass ratio gives you 1.046 for 13 and 12, which tells you that the B ratio is off by 5%. So you're going to see a change in the spacing of the lines. You'll see a change in the position of the band center. So you can predict where this is going to happen, or you can make the measurement and then say something about the, so in my lab course, I don't tell them there's carbon-13. They have to figure out what it is, and they have to find the mass, and they get it within 0.1% or so. So there's the isotope effects that perturb this. There's carbon-13 down here. Isotope effects. Here's a second example for hydrogen-chlorine. So hydrogen-chlorine, the isotopes would be 35C or 37C. They don't differ by very much. So the shift in the band center is only 2 wave numbers. But you can see immediately if you use the spectrum to determine the parameters or use the parameters to calculate the spectrum. Here's what it actually looks like in the laboratory, HCl. Heteronuclear, so if you look in there, you can see the slight offset of the lines. Here's the center, null gap. Now, this is the high frequency side in energy units. So is this the R branch or the P? High energy, R is longer than P. You know right away, that's the R branch, that's the P branch. And the first line is going to be R of 0. This one is going to be P of 1. So you look at these spectra, and immediately you can determine the line, the center, the spacings, isotope ratios, anything. Hot bands, okay. So in a hot gas, a combustion gas, you have to worry about the fact that you have, you can have absorption from excited states. Even if the vibrational temperature of the CO is 3,000 degrees, if in combustion you have a temperature of 2,000 degrees, you have a significant Boltzmann fraction V equals 1. So now you're going to see absorption from V equals 0 and also from V equals 1. And it always boils down to the Boltzmann ratio. What's the fractional population in level 1 and level 0? Look at carbon monoxide. The omega is 2143, which means the characteristic temperature theta is that times 1.44. At 300 degrees, the fractional population in 1 is 10 to the minus 4. Insignificant. Ah, yes, but what if I go to 1,000 degrees? Well, now it's 5%. It starts to be important. It goes up fast with temperature. So, for example, if you look at oxygen a little bit lower, it's about 1,500 wave numbers, 1%, even at 1,000 degrees. Look at iodine. Iodine has a really low frequency. It's 0.7. The ratio of N1 over N0 is 0.7. Pretty amazing. So everything always boils down to mass, frequency systems. Okay. So here's the difference between looking at hydrogen chlorine with the big value of B, which means a small value of I. And so these spectra change a lot. So as you go to 300 degrees, 1,000 degrees, they split up, they spread out this way. Now over here, CO, what's the difference? CO has a small spacing, so there's lots of lines. What does that mean? The more lines, the more states that are populated, the smaller the fraction in any one state. So the absorption for HCl is going to be huge in any one quantum state because the molecules are only distributed over a handful of states. So the Boltzmann fraction is really, really important in spectroscopy. Okay, combustion gases. We've been talking about Ro-vibrational spectra. We're interested in this in part because so many of the combustion gases are infrared active. Heteronuclear, CO. So all of these species that we care about, combustion species, absorb strongly in the infrared. This axis is the strength of the transition versus wavelength. You can see if you look at nitric oxide, this one is about O3 carbon monoxide. This one is 100 times stronger than this one, which is 100 times stronger than this one. So in other words, the absorption here is 10 to the 4th of it is over here. So if you want to measure CO, you want to be out here at 4.6 microns. Try to do it at 2.3, it's 100 times weaker. So you have to be aware of where these gases absorb, and you also have to be aware of where they interfere. It looks like they interfere here, but usually the spacing of the lines is such you can find windows. Water, the good news about water is it absorbs everywhere. The bad news about water is it absorbs everywhere. So it's a constant problem. So it's an opportunity and it's a problem. If you go to the fuels, like typical hydrocarbon fuel, it absorbs strongly at around 3.4 microns. That's due to what's called the CH stretch motion. So all of these important species are infrared active. There are, now, but when you go to the big molecules like the fuel molecule, there's no longer discrete lines, they're blended. And we have to deal with those in a different way. Okay, now we're going to zing on and hope my computer doesn't die. Let's see if I can do this. So, what have we done so far? We did rotation and vibration. Which one's left? Electronic. Electronic's more complicated, but it's very important. We use the UV, the electronic transitions are stronger. So the absorption is stronger. So if you want to measure a species like OH, which has a small mole fraction, say 10 ppm, 100 ppm, you better go to the UV. So now we're in wavelengths, nanometers, that's 308 nanometers, or 3,000 angstroms. And this is now strength of the transition versus the wavelength. And what do we see? These are the positions of the lines, the positions of the lines, and then the vertical height is the strength of the transition. Looks like a mess. have to deal with this. So my students spent a lot of time measuring OH. This is the strengths of the lines that are populated at 2,000 degrees Kelvin, and there's a bunch of notation here. I know from this that means that this is V double prime of 0, V prime of 0, the X to the A electronic state. So the X and the A tell me which electronic states I'm dealing with. The 0 and the 0 tell me the vibrational states that I'm dealing with. And then now we got to deal with the fact that there's different J's. Now you look in there and you see there's no longer just a P and an R. Well, it's a little more complicated. We now have Q's, and we have a Q1 and we have a Q2. So it turns out that because of the character of OH, there are essentially 6 strong branches. For years, we have been measuring OH in our shock tube experiments right here, because we had a laser that worked right there. Lately, we realized we need to get a little more sensitivity, so we jumped to here. So it's only in the last year we realized by changing our laser, we could get a line strength that's twice as big. So now suddenly we can detect half as much OH. So you need to understand the spectrum in order to plan your attack on whatever it is you're going to try to measure. So these positions are all known. The strengths you'll have to calculate. There are some tabulations, but they will be at some reference temperature, and you'll have to know how to do them at another temperature. Okay, that's where we're headed. I put that picture up and I tell my students, now we're going to spend 3 weeks for you to learn how to calculate that. That would be the end. If you had that, you'd have everything you need. So we're back to electronic transitions and all the notations. So when you have, there's a capital letter here, capital A, B, C, and then you'll see a 3, and that corresponds to the so-called spin of the molecule. And typically, these will all be a 3, or there'll be another number. And when that number changes, the spin changes, then it'll be so-called spin forbidden, and you'll no longer have capital letters. So the spectroscopists look at this, and they already know what you're talking about. The lowest energy state always has an X. The upper levels are A, B, C, D. They'll either have a superscript here, say, of 1 or 3. And nitrogen is an X1 sigma. That means the spin is 0. This here is the spin is 1, and that's forbidden. So you don't actually have an allowed transition from X to A. So there's a lot of rules, and we're not going to go over all the rules. But there are rules, except the fact that there's rules in every game. Now, where I worried about heteronuclear, homonuclear for rotation and vibration, we don't worry about that anymore. That's no longer a factor. So we're just going to deal with the potential energy wells associated with electronic forces. Remember, this is called the repulsive side. The two nuclei, they start pushing back against each other. The electron clouds are not happy. When you pull it apart, it gets lazy over here. So there's one of these curves for every electronic state. Most of the time, you're dealing with the lowest energy state for nitrogen, CO, whatever. But there's many of them up here, all like this. And they have slightly different values of RE. Because when you change the electron distribution, you've changed the minimum point of the potential energy curve. When you change the minimum value of RE, you've changed the moment of inertia. You've changed B. The spectrum's entirely different. We have to deal with that. You change the electronic configuration, you change the shape and the energy level of the diagram. Here's an example. So you might have the ground state X here. You might have the excited state A here. That would be the first excited state, electronic excited state, with the same spin. As soon as you look at this, you see there's a lot of lengths on these lines. There's the dissociation energy of this state. Here's the dissociation energy of this state. They're different. This is the difference between the energy of the atoms when you pull the molecules apart. There's lengths here between the lowest vibrational level and, say, this one here. And there's all of these lengths are energies or frequencies which we can see in the spectrum. So from the spectrum, you can figure out the energy level structure. Once, of course, the energy level structure is known, you can calculate the spectrum. So it's like a bootstrap strategy. Right now, we're going over these concepts. For the most part, you're going to be trying to follow what somebody else has already done, just trying to understand why did they use the R7 line. So the potential energy wells for nitrogen. A is the first excited state with the same spin, ground. Okay, these lengths tell us already something about what you're going to see in the spectrum. So when we look at the spectrum, we can immediately see what is the spacing between these wells, what is the, from the spectrum alone, we can characterize some of these energies. Okay, so a lot of notation again. Now we use D for dissociation, where D before is also the distortion constant. You have to kind of keep track. So these dissociation energies are different. Remember, we use prime for the upper state, double prime for the lower state. Okay, thinking about molecules and processes, actually in combustion generally, it's always good to think about the characteristic times that you care about. So for example, what is the time it takes for an electron in a molecule to move to a different orbit? We've got electrons, they're light, they're fast. That's a very short time. It takes of the order of 10 to the minus 16 seconds for the electron to be in another orbit. Now, why does it go to another orbit? It might go from an upper level orbit to a lower orbit because it's going to emit light, go from high energy to low energy spontaneously. The time it takes for the electron to move is a short time. What's the characteristic time for one vibration of this molecule? Maybe 10 to the minus 13 seconds. Where did I get that number? That's from the vibrational frequency that we've already just talked about. How about the duration of a collision? How long does it take for a molecule to collide with another one? Well, it depends on how fast they're going and so on. But it's over the order of maybe 10 to the minus 12 seconds. What about the time for one rotation? 10 to the minus 10 seconds. That would be a tenth of a nanosecond. That's interesting. So that rotational time is, say, 3 orders of magnitude longer than this one. The thing's vibrating like crazy while it's rotating slowly. So the frequencies are quite different. Now, what about the time it takes for a molecule to change, to radiate? So if you park a molecule in an excited state and leave it alone, how long before it spontaneously goes back to a lower level? That's called the radiative lifetime. It's the average length of time a molecule spends in an excited state before. And this is something that comes to us through what we'll call the Einstein relations. That time may vary widely, maybe 10 to the minus 6, 10 to the minus 8 seconds. So look how big these time variations are. So you have to decide, what time frame are you interested in? And then you can say, well, because of my time frame, the others are fast, I can assume some kind of equilibrium. You can simplify a problem by keeping in mind the relative magnitudes of these timescales. This leads me to what's called the Franck-Condon principle. So we had the Born-Oppenheimer approximation that the rotational and vibrational energies can be viewed as separate. We have another one called the Franck-Condon principle. And this one is that since the electron adjustment time is so much faster than all of the others, that means that the molecule, which is rotating and vibrating, hasn't moved in the time it takes for the electron to change. That time is so short that you can view that change as taking place at constant molecular coordinates. That simplifies the theory that goes into spectroscopy immensely. Franck-Condon principle. And that just says that the time it takes for the molecule to go from, say, here to here is short. And in that length of time, that just means that these arrows are vertical, that you go from one point to another. You do not change the coordinate distance in the time frame of a version. Where does the molecule spend the greatest amount of time? Imagine you're down here, oscillating. Remember now, this is where you're not moving, this is where you're moving fast. So the turning points are where you spend most of the time. It goes fast in between. So therefore, the transitions that will be favored are the ones that are near the end, because they spend more time there. So there's this Franck-Condon thinking that goes into helping you understand the spectra. Okay, another point. Collision time is of the order of 10 to the minus 12 seconds. It's pretty close to the vibrational time. So it turns out that if you want to have a transition in V associated with a collision, so how does a molecule change V? It has to have a collision, or it has to absorb light. So you're given the level of V, In comes a fast-moving collision partner. Bang. Conservation of energy applies. So some of that kinetic energy can go into raising the vibrational level. Of course, it can go the other way, but it takes a collision. So whenever the collisions are resonant, that is, if they have time scales that are similar, the efficiencies are always higher. So the most efficient collisions are those which have a speed or time that corresponds to the vibrational oscillation time. So molecules change quantum states. They change mostly by collisions. So why is it we have a Boltzmann distribution? That's the equilibrium answer. But how do we achieve it? It's by collisions. Collisions are fast, so in the room right now, the collision frequency is, say, 10 to the 9th, 10 to the 10th per second. Nitrogen zipping through space has about 10 to the 10th collisions per second. So there's enough of these collisions that some of them are enough for it to change quantum state. And this happens so fast that there is a temperature. If you lower the pressure way down, you can encounter some non-equilibrium, meaning you violate the Boltzmann distribution. So it's the collisions that are responsible for maintaining the Boltzmann distribution. Okay, so there's discrete spectra and there's non-discrete spectra, continuum spectra. So here's an example of two potential energy wells. So I picked a case where this Re prime, double prime is the same as Re double prime. What that means is that there's a lot of opportunities for molecules near one end of this distribution to find a partner up here. So the Franck-Condon principle says that whenever you have good alignment, you're going to have highly efficient transitions. So where's the, in rotation we had delta J is 1. In vibration we had delta V is 1 and delta J is plus or minus 1 for our simple molecules. When we go to electronic systems, everything kind of breaks down, it gets more complicated. It depends upon Franck-Condon principle. I can't give you any simple answers. There's no longer a specific delta V and a specific delta J. It depends on this Franck-Condon principle, which varies from molecule to molecule. Okay, I'm going to just show you a couple of examples of what you would see in a spectrum. So consider a case like this. So if we had transitions here now, this is now absorption versus frequency. Nothing can happen. Let's say you're all in V double prime 0. Nothing can happen until you have enough energy. Nothing can happen until you reach new zero, going up in frequency. As you go up, there's a lot more possibilities. But assuming you're starting here, you have to have this much energy minimum to see an absorption. So you'll see some sort of structure as you populate different vibrational levels. Until you reach the place where finally, from here, you got sending in so much energy that you dissociate this molecule. So now you'll start seeing a continuum spectrum. So if I saw the spectrum, I could already guess something about this energy level structure. Now, you're not going to use this to calculate the spectrum. I'm just trying to help you understand why spectra sometimes are discrete, sometimes they're continuous, but they relate just to the energy level structure of the molecule. Now, there's another kind of state that's a little confusing. Usually, the structure of the molecule is like this. This is now the potential energy in this electronic configuration. There are some cases that look like this. They're called repulsive. These are called attractive. These are called repulsive. What's happening is that these two atoms are coming together, and they don't like each other at all. Why? Because the spin of one of these things is unhappy with the other spin. In this case, they like each other, and they pull together. So let's imagine we have two atoms that come together along this path, and they'll start going down this path. If, in that process, there's a collision or something that takes away some of that energy, it'll get trapped in this well and it'll never go back. But in this case, they come together until they run out of steam and then they go back out. So this is because of the electronic character. That's called a repulsive state. And that repulsive state leads to a difference in the apparent spectrum. Instead of it looking like this one, it'll look like this one. So again, this would be a clue that there was a repulsive state. Or if I had a repulsive state, there'd be an expectation of this continuous distribution. This is the example that comes back from my lab course again. This is what the students do in like week 2, I think, of my course. This is the emission spectrum from air, low pressure discharge, and you can see all these features. So gradually now you're beginning to understand. This must be, I don't know why that P branch is there. This must be a particular electronic system, and it's for particular delta V. For some reason, this delta V of 4 is favored because of the Franck-Condon principle. So that's telling me something already about nitrogen of this. Okay, now the hard part about electronic spectra is the rotational part. We no longer have these simple rules that we had before, and so we have to bear into this analysis a little bit to understand the spectroscopy. Remember, the frequency difference is what we're after for the line positions. But now we have to combine rotation, the vibration, and electronic energy. So we have F, G, it's usually a T. Here's our rigid rotor term, here's our anharmonic oscillator term, and here's electronic. So we sum up the energies independently. We do the same thing for the lower state, and recognize that we're going to see clusters of lines that we'll call a band. And if we look in that band for the 2 states, the upper state and the lower state, those are constants for that band. The only thing we're leaving out is J. So what I'm going to try to show you is how complicated it is to deal with the rotational part of this problem. So you take the difference between the upper and the lower states, you write it in terms of the B's and the J's. C is that's the difference between these constants. This is now for a single band, meaning I have specified V prime and I've specified V double prime, but I have not yet specified J. When I do that, all these lines fall into this pattern that's called the 4-track parabola, that there's a constant, which is the difference between these C's, and things that depend upon J using this trick. If you write M as either minus J or J plus 1, all of the lines in P and R combine into a single equation, where A is the difference in the B's. Remember now, this is B upper, and this is B lower, but this is a different electronic state. So this A could be a pretty big number. And it can be negative. And this little b is the sum. That's a positive number. So now you can ask, well, where's the band head? If I take the derivative of this expression here, I can find out that the band head in M is minus b over 2a. So the band head is delta b over this delta b. So I can immediately see whether the band head is positive or negative M. So the band head is not necessarily in the R branch. It might be in the P branch. Depends. If the upper state has a bigger internuclear spacing, then it will have a higher value of moment of inertia, and it will have a smaller value of B. Alpha is negative, A is negative, and the band head is in the R. But if it's the other way around, that the internuclear spacing is smaller in the upper state, the band head will be in the P. So immediately, as soon as I see the spectrum, I can tell, I see a band head. I immediately know something about this molecule that you can see. Here's an example. Here's oxygen. The ground state has a value of B, a double prime of 1.44. The first electronic state that we care about, because it has the same 3, has a value of B that is quite a bit smaller. Now, because of that delta B up here, big difference. You can have an extreme, you can have a band head at very low J's. In fact, the band head will be at M of 3. Now remember, M is either J plus 1 or it's minus J. J plus 1, so this is a positive number. The band head occurs at a rotational quantum number of about 2. So it looks like this. So this is the 4-track plot. This is frequency. Look at these units, 20,000 wave numbers. Not 2,000 anymore, 20,000. So if you plot these lines on this parabola, you see here's the null gap, and here's the band head right here at very low values of M. So the spectrum changes a lot when you go to, I should say one more thing. When we work with the infrared, we call it Ro-vibrational. When we combine rotation, vibration, and electronic, we call it Ro-vibronic. It means it's a combined rotation, vibration, electronic transition. Now the question is, we're trying to understand the positions of the lines. How do we do this? I'm going to show you how we do this. You won't ever have to probably do this, but you should at least see how it's done. First thing you have to do is you have to try to label the lines and give them the quantum notation. Then you have to take the spacings and you figure out everything. And there's a few ways to do this. But basically, the simplest thing is if you see a band head, you'll know immediately whether it's in the long frequency or short frequency. You'll know immediately whether it's P or R. So if you find a band head, there's an overlap with the lines, but there's a strategy. It's more complicated. If there's no band head, it's obvious. There's a null gap, you're done. R branch, P branch. But if there's a band head, you've got to decide how to count the lines. And the strategy is you go out to the wings and you work your way back in. I'm going to show you quickly because we're a little bit behind in schedule. So here's the homework assignment I typically give the students. This is a listing of the positions of the lines. So somebody did the spectrum of this molecule. I don't remember what, oh, here it is. It's chlorine. Somebody studied the spectrum of the 35 chlorine diatomic molecule in bands that in systems they believe to be the X to the A. And they saw lines at all these positions. So this is what they looked like on their film. Here's the band head. So they measure those numbers. They know what they started with, is chlorine. Question is, which line is which? What are the rotational quantum numbers? And so how do they go about solving that problem? What's the goal? The goal is always to find the B's. Remember, the rotational part of this problem depends only on the B's, which depends only on these R's. So you look at this and you work backwards. Here's the band head. We know that number. We may not yet know where the null gap is. We probably don't yet know where the null gap is. We're going to find it. Typically what you do is you go to the other end. You go way out here. We're way out there. Remember, this is a bigger number, so that's R branch band head. So you go way out here, and you use what's called the principle of constant second differences. We know that the spacing of the lines is 2b. So you go way out here, and you look at this as, say, two lines, and take the difference, 1.88. Do it again, 1.7. Do it again, 1.53. Now, what does that mean? Those are the differences in those frequencies. If you'll notice, if you take the second difference, you get the same number. That's the principle of constant second difference. If you go out far enough, you're coming back in one branch. And you know that the line spacing changes by a constant amount. That's called T2. And you keep working your way back. And because of that number, you can work your way back. You know that I got to go from 1.53, I got to go to 1.36, I have to go to 1.18, and so on. And next thing you know, you're leaping over lines. And you work your way all the way up to the top and work your way back down, all by the principle of constant second difference. So now that I know T1 and T2, I have the information needed to solve for the rotational constants. And I can label these lines. So I don't yet, when I work my way back, I can find out there's no line right here. There's the null gap. So I'm working my way in the P branch, 6, 5, 4, 3, 2, 1. There's no P0. But I could tell from these numbers already where R0 is. 1, now I'm coming back, 2, 3, 4. So you can do this by working from the extremes back through and using the principle of constant second difference. So that's how you would identify those lines and extract the null gap value and the value for T2, that's 2A. So anyway, you can figure out from this picture everything you need to know about this molecule if you were confronted with having to interpret the spectrum. You can also use this method. Once you've done this, once you've identified the lines, you can use this principle of common upper states. I would take the P2 line and the R0 line, and that spacing right here is 6b. Just determined B double prime. Same thing for the lower states. So you can once you have the line positions, you can identify them and figure out what the values are of all the quantities you care about, U0, 2A, and so on. So I'm going a little fast. You're not expected to master this. You should just see it. It's the method of common states to get at these quantities. Now, so remember we got rotation, vibration, electronics. We may already know the distances between the electronic states from the null gap. We just did the parameters needed for the rotational states. What about the vibrational states? How do we get that? Now we use something else. We use tables of band values. It's called it, excuse my French, I call it the Delandry's table. Somebody here from France may know that I'm not pronouncing that right. But this is a table in which the spectrum is recorded over a wide range, and the null gap values, that is the null gap, are plotted versus the V double prime and the V prime. So basically, this table is populated by looking at the positions of all the null gaps. And what do they depend on? They depend upon the omega E's and the omega X's. So you can use this approach. Remember, the G of V is this anharmonic form, and the delta G's are omega E minus 2 omega XC for 1, 0. Okay, that's here to here, right here, 1, 0. So you pick off the delta, the V's, and you populate this table, and you use this expression, and you can find everything. You will again use this principle of constant differences. So for example, if I look at this quantity right here, which is omega E minus 2 omega XC, whereas this one is omega E minus 4, that difference is 2 omega EX. So basically, I can use that concept. The second difference immediately gives me this correction term. If that correction term is 0, what do I have? Harmonic oscillator. So you go along the rows, and you're learning something about omega, the double prime state. If you go along the columns, you learn about the upper state. So you populate, typically in the exam, I give a partially populated table and say, find everything. What is there to find? There's the omega E double prime and the omega E prime, and there's the omega E XC double prime. So there's 4 terms. So you can find the values in the model from the spectra. You just have to keep in mind the energy differences as a function of in this anharmonic model. Here's an example. Here's the table. Band origin for some air emission spectrum. Doesn't make any difference whether it's emission or absorption. The numbers are the same. So these are just the numbers that could be used in solving for any of these differences. The principle is principle of constant second difference. So you use this for rotations, and you use it here again for vibrations. You look and see, you say you take this difference is 1480. This difference is 1460, 1440. Difference between these 20, 20. Do it this way, 40, 40. So I've immediately got everything I need to know just from the positions of the band center in the spectrum. Okay, to summarize. Doing rotational analysis, you can solve for the B's and the distortion constants. Vibrational analysis, we care about the vibrational frequency in its anharmonic term. Emission analysis, okay, when you do emission, the variable in the problem is the lower state. Emission is how you study the lower state. Absorption is how you study the upper state, because it's in the ground state and it's going to different higher levels. So there's a strategy for all of this stuff. And the only thing you really need to take away from this is that conceptually you understand this. It's conservation of energy. It's recognition of the Franck-Condon principle, the Born-Oppenheimer approximation, and expressions for the rotational energy, the vibrational energy. They're either rigid rotor, harmonic oscillator, or one correction. So that underlies all of the spectroscopy that we do. Okay. Some people would say, I really care about the dissociation energy. Why? I want to calculate the equilibrium fraction of the atoms. So you have molecular oxygen. Calculate the equilibrium composition. I need to know the temperature and the dissociation energy. So how would I know about the dissociation energy from what we've just been looking at, for example? You could get the dissociation energy a couple of different ways. You can look at some an analysis of the spectra. There's something called the Burge-Sponer method I'm going to show you. There's different ways of getting at the dissociation energy. When I started as a graduate student, a long time ago, I needed to know the dissociation energy of nitrogen because I wanted to study the dissociation of nitrogen. There were two schools of thought. It's either 7.5 electron volts or 9.5. Hard to believe that the dissociation energy of nitrogen wasn't actually known until about maybe 1965. But how could you ever go about finding it? There's several ways you can go about finding it. And there was some confusion in the literature at that time. Final answer became obvious after a while. Okay, so here's what you could do. For example, this is the crude way. Imagine you think of the electronic excitation. Here's the absorption spectrum that you might see. Nothing happens, if you imagine if it's absorption, everything is in the ground states. Nothing happens until you get a frequency that takes you from here to here. Then it turns into a continuous spectrum. That number right there probably corresponds to this overall number from here up to here. So the band origin, you can, and once you have this number, by the way, you can enter this into the de Landry's tables. So there's ways you can use this pattern to try to figure out the association energy or the vibrational terms. Emission. In emission, imagine you're parked up here. Emission, the variable is the lower state. So now you look at this pattern and you can again relate this pattern back to the energies. So the band origin, so you would see different peaks that correspond to different lower vibrational levels. So that's how you would get the numbers that go into that table. I'm going pretty fast because I want to keep us on time here. We're back to this pattern again that I've shown you like 4 times. So somehow people figured out that this is 6 and 2, that delta V of 4 was favored, and from these numbers, you can calculate this from these values of frequency. You can figure out all the parameters that are missing. So you can use emission spectra, you can use absorption spectra, and you can figure out things that you don't know. Or let's say you took say an emission spectrum from a simple combustion problem, say a couple species. Look at the spectrum. You can see, well, what species are present? What is the relative proportions of these species? So the emission spectrum might tell you quite a bit. The absorption spectrum might tell you something too. So the spectrum would tell you what species are present, what is the temperature, or maybe you would be calculating the same. Spectra can look kind of complicated. This is, in the old days, people used what's called a Geissler tube. This is a low pressure discharge, DC voltage. Electrons are bombarding the atoms or molecules. Light comes out. That's the easiest. So if you're interested in line positions, you don't care about the line strengths. Line positions, people would study, let's see, this is air. So this is how they found out the nitrogen and the oxygen lines. So these are wavelengths in nanometers, angstroms rather, 2800. So the pattern of lines, so see here's the pattern that they attribute to delta V of 2, 1, 0, -1, gamma bands. So people would study these things, study these things. Maybe they switch the gas. Eventually, they figured out everything you need to know. The electronic excitation energies, the vibrational frequencies, the rotational, everything is fixed. But remember, this is really line positions. Line positions, their strengths, and their shapes. You need all 3 to do modern spectroscopy. So a lot of people spend their entire lives just dealing with this because from these spectra, you can determine the molecular properties of these molecules, that is their configuration and their... Now, these are diatomic molecules. What happens when you go to triatomic? It's a lot harder. Everything gets harder. Okay, now, we want to do the dissociation energy, and I want to show you a couple ways that this can be done. There's a famous method called the Burge-Sponer method. This method says that the vibrational spacing in our simple anharmonic model Here's G of V, and there's the anharmonic correction term. Here's G for V plus 1. What if you take the difference? You get 2 omega E XE and then in this other term. So in other words, this is you get omega E, and then you get correction for the omega XE. If you plot it, if you write it this way, you see that delta G can be thought of as this is AV, this is V, AV plus B. So it's a linear equation. So the assumption is made that if you like that molecular model, delta G is a linear function of V, and you can plot it this way. You can plot delta G. This is the value between 1 and 0, and it gets smaller and smaller and smaller and smaller, and you say, when it goes to 0, that's the dissociation energy. That's an approximation. That allows you to find the dissociation energy simply from the slope of this line, initial value and the slope. So you find the dissociation value, the value of V at the dissociation limit. So this is a simple model. It's not really very good. It's a way to help you think. You can solve for dE this way, and it's roughly omega E over 4 XE. So from the slope of this line, you can get essentially everything. This is a way to get the dissociation energy, at least approximately. Or you can think of it as the area under the curve. Doesn't make any difference. Now, the real case. What's the real case? The real case is that as you go up in V, it becomes more and more anharmonic. The result of that is this simple model over-predicts the dissociation energy by 15, 20%. Here's the example. Here's hydrogen chlorine. If you take the spectra, the first few lines, you can solve for these numbers, and you get 513 kilojoules. The dissociation vibrational quantum number 27. The reality is like 427. So this always overestimates the answer. The Bird-Spooner always overestimates. But the only reason I show it to you is that when you want to get a feel for how does the dissociation energy vary with the vibrational frequencies? How do these molecules behave in dissociation energy relative to their spectroscopic properties? Here's the approach that I like. It's called the thermochemical approach. So imagine you have a reaction here. If you assume chemical equilibrium, the equilibrium constant is the partial pressure of the products squared over the partial pressure of the reactant. And then there's something called the Van Hoff relation that tells you how the equilibrium constant varies with the delta H of the reaction in terms of temperature. So we know this. This is like the fundamentals of thermochemistry. So what does that mean? That means if you do an experiment at known temperatures and you measure the partial pressures, you've just determined the dissociation rate. Well, you've determined delta H, which essentially is the dissociation energy. So you can use this, and it actually turns out to be a really interesting strategy. I'm going to show you how we came onto this problem. For years, we measured OH versus time in shock tube experiments. So some sort of this experiment at 2600 Kelvin, hydrogen, and oxygen. For years, I would tell new students, go and measure OH by laser absorption until you get an answer the same as we got for the last years. Students would go out there, and after a while, the students were getting consistent answers, but when we calculated it, it was different than in various simulations. Finally, I decided, there's something wrong here. Be careful about how you do this. We measured the parts per million that we formed, and we found that in order to explain these plateau levels, we had to change the heat of formation of OH. You would think that the heat of formation of OH would be known amazingly well. But about 12 years ago or so, maybe 15, we postulated that it was an error, that it was off by some amount here, about 0.6 out of 9.4. That was the only way we could explain our answers. We felt that we were measuring the OH accurately. And we knew that we had the initial values of hydrogen and oxygen accurately. So how can we have an inconsistency? Either the spectroscopic database is wrong or the thermochemistry database is wrong. So we postulated this, and by chance, it turns out, so we modeled this using GRI mech, which is a traditional mechanism, using the embedded thermodynamics database for the heat of formation of all the species. What we found is that the only way we can reconcile our measurements is if we change the heat of formation from 9.4 to 8.9, 5 or 6% change. And by chance, at almost exactly the same time, a thermodynamics expert at Argonne National Laboratories decided that to be consistent with all of the thermodynamics data that he had in his database, also that this had to change. So by chance, well, by chance, it's science. This is the way science goes forward. There was, here was the GRI MEC database, which was based upon a heat of formation that came from somebody in 1989. Here's the Sandia database that came from the Janif tables, 9.4, 9. You might think that these numbers are known. Where did they come from? You get the heat of formation of OH. You can't do a calorimeter experiment. Exactly. So it comes back to spectroscopy is a tool to study stuff. So, of course, we get the spectroscopic parameters sometimes from, so it's all like a, it works together like a, you go round and round. So these databases which came from somewhere were wrong. The new value, which was Branko Rusick, 2002, I guess it was. We were perfectly, now he was examining all of the data in his database for all sorts of things. He figured out, he called it the active thermochemical tables. But he agreed, so there was a case where the spectroscopy revealed this problem. Anytime you do a chemical kinetics calculation, you specify the reaction, you specify the rate constant, and then you specify the heat of reaction. You don't get that heat of reaction right. Your reverse rates are wrong. So all of this, you know, you make an improvement here that fixes it over here, and spectroscopy, where did the values come from in, say, the Janif tables or whatever thermodynamics database that you have for the energy levels of, for the heats of reaction or the specific heats? Came mostly from spectroscopy. Use spectroscopy to determine the molecular parameters, and then use theory to determine the parameters you care about, like specific heat. Okay, I somehow went at record speed. Sorry about that. But at least my computer didn't crap out on me. Okay, questions. So we're covering a lot of ground because I think you should see the breadth of spectroscopy, even though when you do it in your research, you're going to be in some little niche. Maybe your job is to measure water with a diode laser. And now you home in, follow what somebody else has done, try to understand it. But you should be aware of how we got there. Simple model, mechanical models with some quantum mechanics, and you're good to go. Yeah?
Does the index of refraction for gas-phase species come into play?
Yes. Index of refraction is related. So index of refraction has it's a complex term. It's got a real and imaginary part, and they're related. So, for example, in the position of a line, the refractive index gets kind of complicated. Okay. But all of this comes back to electromagnetic theory interaction. It all, you know, the physicists will write it one way, and electrical engineers will write it another way. But in the end, it's just how does light interact with matter? Any other questions? I think somehow we're about 7 minutes ahead of schedule, so I'm sorry for going so fast. I'm happy to take any questions, or you can hang around for a few minutes if you want.